Good afternoon, everybody. Welcome to the second lecture. Yesterday, just as a recap, we discussed the need for particle detectors, right? Because the notion of particle as a Fock excitation is observer dependent. So today, I'm going to introduce the Unruh DeWitt particle detector model and then compute the response of a detector in some specific situations. And part of today's lecture were based on Eduardo Martinez, who is my supervisor. RQI course, the version of this year actually, and his course is also available on Pearson. Okay, okay, let's start. So what is the Unruh DeWitt particle detector model? I'd say that is a very simple model of a particle detector, but despite being simple enough that we are capable of doing calculations with, it can still capture very relevant physics. So let's see what it is. So it's going to be a quantum system that locally interacts with a quantum field. Now, this quantum system, often we just consider some non-relativistic quantum system. And but we can also consider a QFT in a cavity. All right. Here we're going to stick with this non-relativistic quantum system because it's way more explored in the literature. Now, this detector must have some free Hamiltonian, right? There's a free Hamiltonian. Which I'm going to call just HT. And of course, I can have this spectral decomposition. And on top of that, I will prescribe some interaction Hamiltonian between the detector and the field, right? So I will write the interaction Hamiltonian in the interaction picture that I'm gonna prescribe. Okay. Um, well, I will first give you the covariant prescription. And if you are interested in reading a little bit more about that, I'd recommend this paper here. Here. Which was written by my supervisor, Eduardo Martinez, in collaboration with two of his students that already graduated by now, Thales Perch and Bruno Torres. So this prescription is given by the interaction Hamiltonian for some time t. It's going to be the integral in the Cauchy slice for t times the determinant of the metric written in those coordinates times some Hamiltonian weight. And this Hamiltonian weight is given by so I'll have some coupling constant. So this is just coupling constant or coupling strength. So what it tells me is basically how strong is the interaction. Wait, I'm just seeing there's a question in the chat. potential, which, the code for this code? You're saying the archive number? Okay, this is the archive number. I can also type on the group chat if you want, in the Zoom chat. 100. There it is. Okay. Okay. So I'm gonna have this coupling constant, and what it tells me is basically how strong, um, quote unquote, is the interaction, right? Now I'll have some space times mirroring. So this is the space times mirroring function. And basically what it tells me is the spatial temporal profile. Spatial temporal profile of the detector. Now I'll also have some monopole moment. So just, I think it's obvious that I'm multiplying all of these items. Okay, I'm writing just with a lot of space between them so that I can write notes, but everything is multiplying. Um, then I'll have some monopole operator or monopole moment operator. Monopole operator. This is just a detector observable. Detector observable. Okay. And here, this down here is just the detector proper time. Um, on top of that, I need to couple this to some quantum field observable, right? So I'm coupling to some observable of the quantum field. Let's see another color. Uh, This. This is some quantum field observable. Okay. And usually what we consider is that this quantum field observable is just going to be the field amplitude, okay? It's not the only choice. Sometimes we can have coupling to the momentum, for instance. But this is the most common choice for sure. Now, in the proper frame for the detector, in the proper frame of the detector, oh, I mean, most correctly, detector central mass, right? We can use Fermi normal coordinates. Which I would denote by tau x bar. And in those coordinates, what I can observe is that the space-time is mirroring that I just wrote up here, okay, this lambda x, is gonna decompose into some switching function. So this is the switching function. And what the switching function is gonna teach you, basically tell you, is how long the interaction is gonna last, and basically how you turn it on, how you turn it off, this whole time interaction profile. So I'm gonna say that this is how long the interaction lasts, and how sharply Um, it is turned on and off. Okay, so there are several prescriptions for switching function. Uh, some that come to mind would be a delta, which would describe some instantaneous coupling. So instantaneous, instantaneous interaction. Uh, Also Gaussian. Gaussian is really commonly used. Lorentzian. Top hat. And also you can just keep your detector always on. Of course, there are more options. There are several options. Now, as I said, the space times mirror is going to decompose into some switching function times the spatial is mirroring function. So this is times f of the spatial components, right? So this is spatial mirroring function. Again, we are multiplying the two. Um, what it tells me is basically what is the shape of the detector. Okay, so for instance, it could be a box, it could be a sphere, and it could also be point-like, which is the delta in space, right? Okay. Um, okay, I guess we need to make a comment here. The comment is that the point-like detector, oh, sorry, the point-like detector um, is very frequently used in the literature. In the literature, but it's basically an idealization. It is an idealization. So the way you could think of a point-like detector, the proper way of thinking would be as a limit of some detector that has a finite size when the size just shrinks, goes to zero. So I would think of a sphere and then just take the radius to zero. That's how you would think of a point-like detector properly, right? Because realistically, you're gonna have some dimension, right? If you think of an atom, for instance, you could have some dimension. So that's just an idealization, a simplification, right? And that is a limit of a small detector of finite size. There's a question, let me see. Um, so what is this lambda gives you is basically how the detector interacts, right? So how it is distributed in this space-time. So I guess the easiest way to think would be exactly in this situation in which there is a splitting. So when you are using Fermi normal coordinates, because then it's just the shape of a detector. If I have a sphere, you'd expect that this sphere would be rigid, so it's moving. It can move through space, but still like be, uh, behave as a sphere, right? And then there's some coupling time, so you can turn it on for a while and then turn it off. Sometimes you can turn it on very quickly and then turn it off very quickly, or turn it on smoothly, which is a bit more realistic. Um, so I would say this is just describing exactly how this interaction will go. How the characteristics of this detector in terms of the shape, but also how for how long and in how smooth or how sharp it's gonna interact with the field. I hope this is clear. Okay, good. Um, okay, so that being said, the fact that finite size that point light detectors are a bit of an abstraction. From now on, we're gonna focus on them. So um, from now on, we will focus on only with detectors that are so often is the case that people use qubits. So of course, when I said earlier here that in principle I just want some either a non-relativistic quantum system or a QFT in a cavity, and even if I'm just restricting to non-relativistic system, I could have like a harmonic oscillator, a Q tree, any Q that, um, pretty much whatever you wanted. But I think for simplicity, most often people use qubits. Okay, so we're just gonna use qubits uh, that are point light detectors, as I just said, and we're gonna have this couple to the field's amplitude, as I also mentioned that is the most common case. Okay. Now I will write for this particular case how the interaction Hamiltonian looks like. So in this case, the interaction Hamiltonian, the interaction picture is going to be given by. So we'll write as a function of the proper time of the detector, and that is going to be the coupling constant times the switching times this monopole moment and coupled to the field amplitude, which is sampling along the detector's trajectory. Now, specifically for the qubit, what is the free Hamiltonian that we're going to prescribe? So we're going to write some energy gap over 2 times sigma z plus the identity. Sigma z, here is the Pauli z, okay? Let me just write, here is the Pauli z. Let me see a question. Um, yeah, your question is interesting. I guess I cannot think of every situation in which a spherical detector would see a particle, but not like a box-shaped one. But there are some situations like for UV regularization that some prescriptions for this shape of the detector would be important. Like there are some situations in which a point light, for instance, is going to lead to some UV divergences. Then you can use for some finite size, for instance, like either a box or a sphere. Um, and then that is going to regularize your situation. But between spherical and box, I don't think I can see an easy case in which one would measure, but not the other. It's nevertheless gonna give you a different a different result, right? Because the results are gonna depend on what you're prescribing. So you're not gonna get the same exact result, but I guess physically, uh, maybe depending on the symmetries of your situation, one is preferred or the other. And yeah, that's what I would say. Hopefully that helped. Um, okay, so here I can rewrite this as the energy gap times the raising operator for the qubit times the lowering operator for the qubit. And I can rewrite everything as the gap times um, this excited state. So here is the excited state. Okay. Now I also need to prescribe some monopole operator, right? This monopole operator here is going to be, I can basically, physically, what it makes sense is to select some operator of the of my qubit that does not commute with the free Hamiltonian. The reason for that is that I want some non-trivial dynamics. And because I selected something that is proportional to sigma z for the free Hamiltonian, it makes sense to select either sigma x or sigma y or some combination of them. The most commonly used would be sigma x. So because I am in the interaction picture, I have to write the, the time evolution for the free Hamiltonian dagger times my operator, which is sigma x, as I said, and then again the time evolution of the free Hamiltonian for the qubit. Okay, so in this case, what it boils down is to I ht times tau and sigma x e to the minus I ht tau. And that can be written as e to I omega tau times excited ground plus e to the minus I omega tau ground excited. And just to clarify, this G here, as I said, is the ground state. Okay? Uh, that's a good question, Jenny. I don't know. I don't know. I'll try to Google that. Maybe I knew at some point and I don't remember, but I'll Google and then I can answer tomorrow. Um, Let me see. Okay, so given that I already have this free Hamiltonian for the qubit, I have defined what it was going to be my monopole moment. What I need to, given that I have already my interaction Hamiltonian, what I need to evolve my states is a time evolution operator, right? So I need the time evolution operator. And so the time evolution operator, so is going to be given by the time order with respect to tau, the time order exponential of minus I integral over tau of my interaction Hamiltonian. Okay, does that make sense? Let me just right here. Okay. Now, in order to proceed, we need to series expand this operator. So, to proceed. We must series expand this operator. And to do that, I can think of two possible ways. One of them would be the so-called Magnus expansion. And the other one would be the Dyson expansion. Okay, so let's start with the Magnus expansion. The Magnus expansion. So the Magnus expansion would say the following. If I have this u, the u is going to be given by some exponential of this sum from j equals to 1 to infinity of this omega j's, okay? Where this omega 1, maybe let me write it to the left because some expressions are long. This omega 1 is going to be given by minus I times the integral over the whole space of the tau of h of I of tau. Now the second order is going to be given by minus a half times the integral from minus infinity to infinity of the tau, and then the integral from minus infinity to tau of the tau prime, okay? Let me just emphasize this. Of the commutator between hi of tau and hi of tau prime. All right. And then the next order is going to be given by I over 6 times the integral from minus infinity to infinity of the tau. Then again, it's going to be minus infinity to tau instead of infinity here of the tau prime. Then minus infinity to tau prime of the tau double prime. And then I'll have a sum here of a nested commutator. So I have hi of tau commutator with the commutator hi of tau prime with hi of tau double prime. So this nested commutator plus another nested commutator, which is going to be hi of tau double prime with the commutator of hi of tau prime and hi of tau. So this commutator, that commutator, then close for the sum. And then you can continue this. So, well, I will ask because maybe someone has an intuition. When do you think this is going to be very useful? When does this look nice? Any ideas? I'm not sure if anyone is typing. Okay, so I'll say the answer. So the Magnus expansion is particularly useful when it truncates, right? So when would this truncate? When one of these nested commutator is gonna vanish, right? So if one, at some point, one of these nested commutators is a C number, so it's just a number times identity, then the other orders are going to vanish. Does that make sense? So some of the um, sum of this nth order nested commutators is a C number. Okay, so then in other orders, uh, we won't have any contribution. So in this case, we're going to obtain some exact solution. And exact here means in a non-perturbative way. Expression for this time evolution operator that we're after. Okay. Now, there are some situations in which this happens. So in particular, this is going to be the case for gapless detectors. So if you go back into the expression that I gave you, if you just think about gapless detectors, it means just that the two levels, the ground and the excited state, have the same energy. Okay, that is basically the definition of the gapless detector. One feature of these gapless detectors would be that, remember that I mentioned to you that this monopole operator, what I generally want is that this sigma x here, or like some other operator, just gonna is going to not commute with the free Hamiltonian. So I want some non-trivial physics. When I have gapless detectors, it's exactly the situation in which they do commute. So the free Hamiltonian and this interaction Hamiltonian are going to commute this monopole operator. So some people criticize that as being less physical or less realistic. So and then there's also another situation, which is when the switching function, if the switching function has some delta profile, which I mean by this is exactly that the switching function is just going to be some delta. It's just going to couple at one instant of time. This is also, people argue that these are also not very realistic, right? If you're doing an experiment in your lab, you're not going to couple something as a delta coupling, right? Like just in one instant of time. There's always going to be some time, some finite time of interaction. So as I mentioned, there's some criticism that gapless detectors and delta switching are less realistic or less physical. But nevertheless, people do use it, and it has some advantages. One of them is that exactly what I said, right? Having this exact solution, and you can actually use the formalism of algebraic QFT, which is quite nice. And some, if you want to read a little bit more, Some papers that use those types of detectors would be this paper by Landulfo. Is it six? Yeah, 641. And then one paper I'm gonna mention one paper by Eric Santijoa, but he has a few using those non-perturbative approach. 294. Okay, so do you guys have any questions so far? I know it's a lot. I feel like throwing a lot of information at you guys. There's a lot of definitions and I don't know. So ask questions if you want. Now, what I wanted to say is that, however, in the general case, um, we have to resort to the Dyson expansion. Okay, which is going to be for small coupling constants. Um, and when you have a Dyson, one property of the Dyson expansion is that the probabilities are conserved at ever order in this perturbation theory. So, in which the probabilities are conserved in every order. Um, and well, what I mean by this is basically that the corrections are traceless at every order. So we know that density matrices have to have a trace one, right? Be trace one. So this trace one is going to be guaranteed by the zeroth order correction, right? So the initial state has trace one. All the corrections are going to be traceless. So, and the majority of the literature in RQI uses perturbative uses this perturbative case. So let's see what is the Dyson expansion, right? Okay, so the Dyson expansion is going to tell me that this time evolution operator is going to be the identity plus some first order correction, second order correction, and then so on and so forth. I'll just go up to second order. And then let's define what is each of these terms. So the first one is going to be minus I times the integral from minus infinity to infinity of the tau of this, the interaction Hamiltonian of tau. Then the second one, no, it's going to be given by minus integral between minus infinity and infinity of d tau. Again, minus infinity to tau of d tau prime. And then here I just have hi of tau, hi of tau prime. Okay. Now I'm gonna rewrite this in a way that is gonna be a little bit more useful for us in the future, which is just saying that I will integrate over the whole space. So here I'm changing for the whole space, okay? And then I'm gonna introduce a heaviside step function and then times the interaction Hamiltonian of tau, interaction Hamiltonian of tau prime, okay? And let me just define this. So where the heaviside step function or theta function is defined as the following. So the heaviside of x is going to be given by 0 if x is smaller than 0, and then 1 if x is greater than 1. Okay, so here what I'm saying is basically that this heaviside here, when I have tau minus tau prime greater than 0, it means that tau prime is smaller than tau, which is exactly what we had here. We're going to integrate from minus infinity to tau, right? Okay, so I'm just rewriting exactly the same thing. Right. Please let me know if you have any questions, okay? Or if I'm going too fast. Okay. Now, um, finally we have the time evolution operator, right? So we want to compute what is the final state, right? So if the initial state of the system, of the detector and field system is, say, rho 0, which is going to be some initial state of the detector, tensor product with some initial state of the field. Okay, so we generally assume that they are uncoupled to start with, right? So then the time evolved state what is going to be the time evolved state? So the final state is simply ui times the initial state, ui dagger, right? Now, if I'm going to expand this into the terms that we have here, what we have is, well, first, if I'm just acting with identity on both sides, I'm gonna get rho 0. Then I can act with u1 on one side and then identity on the other side, or rho 0, identity on the left side, and then u1 dagger on the right. Or to get the second order corrections now, we would act with u1 on one side and u1 dagger on the other side. I forgot this eyes. Okay. Or I can also act with u2 correction on one side and identity on the other side, or identity on the one side and u2 dagger on the other side, plus higher order corrections, right? Okay, so obviously this is just, the first one is just a zeroth order contributions, right? Just the same thing. So here it would be the first order contribution. And then here I have the second order contributions. Okay. Um, Now, if I'm interested in the final state of the detector instead of being interested in the final state of the detector and the field, and most of the times we're interested in the final state of the detector itself because we're going to measure the detector, right? So the final state of the detector, how would I do that? Any guesses? Maybe if someone has everybody taken any quantum information course? Maybe I'm just talking about density matrices and other things, and you guys are not familiar with. But if someone is familiar with quantum information, how would I just compute the final state of the detector if I'm not interested in the final state of the field? No, I'm going to discard. I want to discard some state. How do I generally do that? Exactly. Partial trace. So what I'm going to do is just say that the final state of the detector is going to be simply the trace over the field. So I'm just partial tracing, right? Tracing out the field degrees of freedom only. So I'm gonna trace out the field times whatever quantity I had before, right? Right? So if I want to compute that, of course, the zeroth order correction is going to be just what I had in the beginning for the detector. Then I'm gonna just write exactly what I had here, but just tracing out the field, right? So I have the trace over the field of U1 times rho 0 plus rho 0 times U1 uh, dagger, which are the first order. So again, first order contributions or corrections. And then I'll just take the trace over the field for whatever I have there. So this here plus the ones that depend on U2. Mm. And then up to some lambda 3 corrections. Okay, this is the second order. This is clear. I hope. Oh, okay, good. All right, with all of that, I guess now we are ready. We are going to compute the response of a particle detector. Okay. Okay, so we're going to start with a qubit. So just as I had mentioned before, um, a qubit detector initially on the ground state. And I'm going to denote this. Okay, let me see the question. So the way that we discard some some system that we're not interested in is basically by this partial trace operation. So if I have like a system A and then a system B, I evolve them, maybe they are interacting with one another. But in the end, either I'm not interested in state B or I just don't have any information. Maybe I gave this to you and I cannot say anything about that anymore. So the way that we do that is this operation is just by partial trace. Okay, so that is a concept from quantum information. So I hope that is clear. I can send you some, I don't know, some notes if you want later. Just email me. Okay. So we're gonna start, as I said, from this qubit, which is originally in the ground state, and I'm gonna write this as 1000, which means that this density matrix, right? Which means that I chose the basis ground, excited. Okay, this is the order of my basis. Um, so that's how I'm going to represent this density matrix. And let us compute its final state after interacting with the field in some state. So here I'm just going to write some general state, okay? For the field. So in other words, the initial detector field system is going to be simply the tensor product between the two, right? So I just have some the initial state of the detector tensor product with the initial state of the field. Okay. Now, as we wrote before, the interaction Hamiltonian is going to be lambda chi of tau, general case, so times mu of tau, tensor product with the field x of tau. Okay. Now, if we, okay, as a reminder as well, and let's first write the time evolution operator. So that was first identity plus first contribution plus second plus some higher order corrections. And in our particular case, what we have for this interaction Hamiltonian is going to be for the first order minus I lambda times the integral from minus infinity to infinity of the tau times pi of tau, mu of tau, and tensor product with the field amplitude. Okay. Now for the second order correction, in our case, what we have is minus lambda square, then the integral from minus infinity to infinity of the tau, integral from minus infinity to infinity of the tau prime times the heavy side, tau minus tau prime, chi of tau prime, then mu of tau prime, and then tensor product here of phi of x of tau, phi of x of tau prime. Okay, let me just have a look in the chat. Yeah, I guess Marcos gave an example if they are separable. Yeah, that's true. If they just have this tensor product structure, that's a good intuition. Yeah. When they are entangled, which is going to be the case here, it gets more subtle, but it's still valid nonetheless. Yeah. Um, okay. So given that we have computed for this specific case, what are the contributions for first and second order? Let's compute the first order contribution um, to the system final state. To the detector field system final state. Okay. So if you think about what we have here, then it's going to be just this contribution as we were before, plus row 0, u1 dagger, but we can also see that this is simply u1 over acting on row 0 plus the Hermitian conjugate of this, right? So I don't need to do both of them. So what this is gonna be, so I'm just gonna write literally whatever I have here for u1. So just minus I lambda integral minus infinity to infinity of the tau chi of tau mu of tau acting over my initial state of the detector, right? Which is going to be 1, 0, 0, 0. And then I have the tensor product on with the field times the initial state of the field. And then this plus the Hermitian conjugate, okay? So maybe I'll just put this parenthesis so that it's clear that it's the Hermitian conjugate of all of this. Now, if I write this mu of tau in the same basis, so I can just write this matrix, what I'm gonna see is that this is gonna be written as 0 e minus I omega tau, and then e to the I omega tau, and 0. That is how I write mu of tau. So when I do this basic math, what I find is that this is minus I lambda integral from minus infinity to infinity of d tau I of tau times 0 e to I omega tau 0, 0. Tensor product phi of x of tau times rho phi. And then I'm gonna get this plus the Hermitian conjugate. Okay? Um, so I will write the first order contribution to the detector now, to the detector's final state. So to the final state of the detector. So as we discussed before, the only thing here is that, of course, I have these two contributions, right? But I'm just gonna have to trace out over the few degrees of freedom. So I already write the matrix form of this. So as I said, just the trace over the field of whatever we just computed, right? So that is going to be, I can write this as 0 sum c, the conjugate, the complex conjugate, the Hermitian conjugate, And um, so where C here, I called it C just to remind you of coherence, but that's just my notation. So C is exactly what I had there. So it's going to be minus I to minus infinity to infinity of this times I omega tau. And now finally taking the trace of I'm gonna write in the order that I like more, which is this. As trace is cyclic anyway, so it doesn't matter. But that's the order that I like. Do you guys have any questions on this part? So basically what I did was just noticing that, well, this Hermitian conjugate par that I have here is gonna give me some e to the minus I omega here, right? So it's going to be exactly and everything else is real. So what I have is just the same term. So this structure of C and C star here. Okay. And again, the trace gave me this part here. All right. So let's move on to the second order contribution unless you guys have questions. Sounds like you're good, or maybe I'm just too fast that you're not following. I don't know. Uh, where? Do you want to speak? Maybe. Well, the identity that you're talking about, maybe I'll try to guess. So the identity that you're talking about is the one that was here. So we had some identity here, right? So as I mentioned before, when I'm going to compute the final state of the detector, the first contribution, the zeroth order contribution, is going to be exactly the same as the initial state of the detector. So that's the part that identity is bringing, okay? But then this first order contribution is only this, okay? All right. Um, we're constrained. Um, so the heavy side here, what it's doing is just literally I wanted to rewrite whatever I had here. So I think the reason maybe it's not clear at this point is gonna be clear hopefully in the next calculation. Because in principle I could just keep this tau here the way it is. The reason I decided to not do it is because there's going to be some identity that is going to be useful for me in my next calculation. So I just wanted you guys to get used to the heavy side at this stage earlier on, rather than introducing everything during the calculation later. Basically, that's it. But I'm just like cutting the limit of the integral short. That's all. Okay, so in some sense, the limits of the integral being in the whole space just looks a little bit more symmetric, so I can do some stuff with it. Hopefully that's clear. Okay, so let's see the second order now. So the second order contribution um, to the detector field system final state. Again, as we saw already, that is going to have some contribution from first order. dagger, right? And then some contribution from you coming from U2. And that is going to be I can also write this as this contribution plus its Hermitian conjugate, okay? Just to reduce your calculations. Now, let's see the first contribution. So the first one. Okay, if we remember, let's see, we had like minus I delta lambda here, and then the other side is going to be with the complex conjugate, right? We want the Hermitian conjugate, so the other one is going to come with a plus I lambda, right? So I'll get a plus here. So it's going to be plus lambda square times the integral from minus infinity to infinity of the t minus infinity to infinity of the tau. And recall that, well, since here we are just acting with u1 on both sides, I don't have any heavy side. Okay, step function. So I will write the switching functions for both of them. Okay, and now I have this monopole moment of tau that comes from the left operator, and then it's going to act on my initial state, and then I'll have another one on tau prime acting from the right. So now for the field, it's going to be similar. So we have a phi of x of tau times the initial state of the field, and then phi of x of tau prime. Okay. And now mu of tau and mu of tau prime are going to be represented by whatever I showed before to you in the matrix form. So if you do the math, what you're going to find, make it a little bit more, is going to be lambda square, integral from minus infinity to infinity for both. And then I have a chi of tau, a chi of tau prime, as I had before. Then the matrix that I'm going to get is going to be 0, 0, 0. And then here I have E I omega tau minus tau prime. Okay. And then in the field degrees of freedom, what we have is phi of x of tau, rho phi, phi of x of tau prime, right? Okay. Now, what is the other contribution? The other one is going to be u, the second order term for u acting on rho 0. Now, let's see what we was. This was some expression like this, right? So I'll have the integral over both full spaces, but I have the heavy side. And notice that here I have a minus sign. So this is going to be minus lambda square, the integral from minus infinity to infinity of the tau, minus infinity to infinity of the tau prime. Then I have the heavy side of tau minus tau prime. Okay. Then I'll get both of the switchings. Okay. And here I'll get a mu of tau times a mu of tau prime acting on my initial state of the detector, right? And for the field part, I'll have a phi of x of tau times a phi of x of tau prime, and then acting on rho phi. So if I do this calculation here, the matrix that I'll get is it's minus I omega tau minus tau prime, 0, 0, and e to the I omega tau minus tau prime. All right, so if I do this math, what I get is minus lambda square, integral from minus infinity to infinity of the tau minus infinity to infinity of tau and the tau prime, then the heavy side, times, I'll get e to the minus I omega tau minus tau prime, 0, 0, 0. And then just repeat whatever I have for the field. Okay. And then, as I said before, if I want to compute the other term, which would be rho 0 ui to dagger, that is simply whatever we computed now, taking the Hermitian conjugate. Okay. All right, so now we want to compute the second order contribution to the detector's final state. To do that, I think I will move to another page because it's kind of long. So hopefully you guys have copied until now. And also if you have questions, let me know. So I'll compute now just a second order contribution to the detector final state. So as we discussed before, this is going to just be the trace, right? That from we just computed. So that is going to be the trace over phi of whatever I had computed. And so we're going to have to have a look into what we had before, right? So from this first contribution here, we had this whole expression. So I will copy it. That's a bit cheating, but I'll copy this expression. So that's what I had here, right? But now I need to take the trace, right? So I'll have to take the trace over this, the few degrees of freedom. So I'll take the trace of this part, okay? And just to write in the form that I like more, I'll write this as, using the cyclicity of the trace, I'll write this as the trace of rho phi times phi of x tau prime times phi of x of tau, okay? Now, let's look into the other two terms. So we had this contribution here, right? So this contribution is gonna give me, let me write here with a lot of space. So this is going to be the second contribution, and we need to again take the trace of this part here. And again, I'm going to rewrite that as the trace of rho phi times phi of x tau times phi of x of tau prime. And then I'll have the other contribution, right, which is the Hermitian conjugate. So let's have a look at what we have. Or actually, let's copy the expression here, and then take the Hermitian conjugate here before taking the trace. So what we had was this, right? But we need to take the Hermitian conjugate. So most of these things are real, but if you look into this part here, uh, this is going to get a plus sign, right? So I'll get a plus sign here, right? And then when I take the Hermitian conjugate here, I will get a row phi first, and then this row of x of tau prime, and then this this phi of x of tau, right? So now finally I can take this trace. So this is the trace that I get here. And notice that this one is already in the form that I like. However, there is one more thing. I would like, if you notice here, let's see look at the order of this. I have here a row phi times phi of x of tau prime times phi of x of tau, which is exactly the same as this last one here. Whereas this one is not the same, right? This one is written as row of phi times phi of x of tau and phi of x of tau prime. I would prefer this order here. I like this one more. So that's kind of a matter of preference, but I like this order. Oh, I like this order more. So that is my favorite. Therefore, I want to change the order, move something here to change the order of this other two here. Okay. So what I'm gonna do, and that's basically why I use these Heaviside step functions, is I'm going to swap tau and tau prime in the first and third terms, okay? So the second, I'm just gonna keep the way it is. Okay, so let's see what we have now. If I just swap, let's see, okay, let me write down. I think it's better that I write down everything so that you guys have the same pace to write. So if I just swap tau and tau prime, you're gonna see that, well, here nothing changes. For chi of tau and tau prime, nothing changes, right? Now, there, here inside the integral, if I swap tau and tau prime, I'm gonna get a minus sign outside, right? So I get a minus I omega tau minus tau prime here, okay? Uh, times the trace, and now inside the trace I also swap, right? So I will get exactly the order that I wanted. So phi of x of tau times phi of x of tau prime. All right. Then the second term, I'm just gonna copy, right? I haven't changed anything there. So I'll just copy it. And 0 times the same trace as I have here. Phi of x of tau, phi of x of tau prime. All right. And then in the third term, I will swap again. So when I swap, I have to swap here inside the heavy side, right? So instead of tau minus tau prime, I'll have tau prime minus tau. And I will also have to swap the sign. So I'll also get e to the minus I omega tau minus tau prime, 0, 0, 0, times the same trace. 。 of x of tau, tau prime. Okay. So if I just sum all of this and use some key property. So if you notice, now what I have here for the second and the third term is, well, this trace is the same, exactly the same, right? Then now this term is also the same, e to the minus I omega tau minus tau prime. So I can combine those two integrals, and then I'm gonna get times this heavy side of tau minus tau prime plus the heavy side of tau prime minus tau. But there is a nice property, which is the heavy side of x plus the heavy side of minus x is equal to 1. Okay? And because of that, I can rewrite everything as simply minus p, 0, 0, p. Because if you look in all of these terms, I'm going to get exactly the same thing. So I have e to the minus I omega tau minus tau prime times this trace integrated against the switching functions. So, and then this p is the probability of excitation. So the probability of excitation is given by p equals to, just basically copy whatever I had there, which is minus infinity to infinity of the tau minus infinity to infinity of the tau prime times chi of tau prime e to the minus I omega tau minus tau prime times the trace. Right? Okay. Okay, so with all of these definitions, the final state of the detector is what? It's going to be final state of the detector, 1 minus p, then I had a c star, a c, and p, right? Plus higher order corrections. Okay, so this is the final state of the detector. So we had this probability of excitation here. So the probability that this detector went from the zero state, from the ground state, to the excited state. And we have also like this first order corrections, which are going to give us these coherences. Okay. And as I said before, of course, we have to, the final state is going to be trace one. It's a density matrix. So everything looks nice. Do you guys have any questions here? Okay. Um, if not, let's have a look into the Minkowski vacuum. So let's see. So far we noticed that these first and second order corrections depend on this so-called 1 and 2 point functions, right? So if you look, where's here? If you look into the first order correction, it depends on this first order, this 1 point correlation function, right? Whereas the second order contribution is going to depend on this 2 point correlator, right? So we want to have a look into what they look like in Minkowski vacuum. All right, so let's see. Um, the field. Remember that we wrote yesterday the field as a function of the modes. So here is going to be the same, but instead of considering discrete modes, I'm going to consider continuous modes, okay? So I'll have that, I can write as the integral over d minus 1k times ak uk of x plus ak dagger uk star of x. And I'm gonna say that x is equal to t, and this other x that is the spatial component. Okay, now we know that the Minkowski vacuum is associated with, so the use for the Minkowski vacuum, the positive frequency modes are gonna be uk is given by, there's a normalization factor here, so it's 2 omega k 2 pi n minus 1, and then square root of everything, and times e to the minus I omega k of t times t plus I k scalar product x, and omega k is square root of k square plus m square. Okay, and oh yeah, such that the associated annihilation operator is going to annihilate the Minkowski vacuum forever k. Okay, so now I state that the 1-point function vanishes. So what I want to compute here is exactly that contribution that came from the first order contribution. I want to compute this 1-point correlator for the Minkowski vacuum, okay? So what I'm gonna do is just take the trace of the Minkowski vacuum times phi of x, okay? And I can write that as, well, the Minkowski vacuum times the field that I just wrote there, right? So this is going to be just the annihilation plus the creation part, and everything acting on the Minkowski vacuum. Now, this annihilation operator is going to acting to the right, is going to annihilate the vacuum, so it's going to get a 0. And similarly, if I have this creation operator acting to the left, it's going to annihilate the bra as well. So what we have is that this is going to vanish. I just have a 0. Okay. And now the 2-point correlator. This 2-point correlator has a special name, which is the Weidmann function. I guess properly, the Weidmann function is associated with, is this 2-point correlator computed in the vacuum. But I guess people use in a more broad sense. So sometimes they would say Weidmann for um, a thermal Weidmann or in other states that are not necessarily the vacuum. But I would say I'll still call it the Weidman, of course. So the Weidman for x prime is going to be exactly these 2-point correlators that we are interested in. And that is going to be phi of x times phi of x prime. Okay, and let's write this. So I have the Minkowski vacuum here. Then I'll have some integral over k, then some other integral over k prime. And I'll write in this other line. So I have ak uk of x plus ak dagger uk star of x. Yeah. Now multiplied by ak prime uk prime of x prime. Yes. Plus ak prime dagger uk prime star of x prime. Okay. And acting on the Minkowski vacuum as well. Now I'll just do a similar analysis to what I had done before. So if I have this annihilation operator acting on to the right, it's gonna annihilate this vacuum. And similarly, this one acting to the left is going to annihilate bra. So basically, the only term that survives is going to be this one times that one. Okay, so let's see. What is this? So this is going to be, I guess maybe I'll just write the integral outside. D minus 1k, D minus 1k prime. And then I'll get a uk of x. I can also pull it out. uk prime star of x prime. And then I have the expectation value of ak prime dagger on the vacuum. So I'll just do the usual trick here. So I'll write this as the commutator between ak prime dagger plus ak ak prime dagger times ak. And again, I'm gonna argue that this one acting to the right here is going to annihilate the vacuum. So the only contribution is going to be from this commutator, which is going to just be delta n minus 1 of k minus k prime. Okay, so this is going to give me, if I integrate over k prime, I'll get just the n minus 1k times uk of x times uk star of uk star of x prime. Okay, and if I write this in terms of the mode, so if I just go back here and just explicitly write what I'm gonna get, this is going to be the integral over d minus 1k times 1 over 2 omega k times 2 pi to the power n minus 1 times e to the minus I omega k. Then I'll get a t minus t prime plus I k scalar with x minus x prime. And that is the final result for this 2-point function for the Weidman. Okay. Questions here. It was mostly calculations, right? But I guess one important comment, maybe I'll just put this a little bit up here so that I can write this comment. Um, okay. So the comment is the following. If you were to compute, what you would see is that all the odd point functions, or odd point functions, will vanish, and all the even point functions uh, will be functions of the Weidman. So functions of the 2-point function. So when this happens, we call this state a quasi-free state. So the Minkowski vacuum is a quasi-free state. Or another nomenclature for this is a zero mean Gaussian state. Let me see what Marcus is saying. Marcus, this is an this is an expectation value as well. This is still an expectation value, yeah. But we generally call this yes, there are many types of 2-point correlators. This is one of them. That is the Weidman function is one of them. There are several. I promise there are so many, but it's going to be special in our situation. Uh, I'm not sure if I understand this other question. Here, like what happened here is we are using both positive and negative frequencies, right? I wrote the positive frequency here, but that one automatically tells me what is the negative frequency. And if you look at my final result, what I have is a positive frequency one for computed in X times the negative frequency one for X prime. Okay, so we're just acting with creation and annihilation operators and seeing acting with them on the Minkowski vacuum and seeing what we get. Okay, so we use both. I just define one of them because the other one is automatically defined based on that. It's just taking the complex conjugate of that one. Okay. Um, Now I wonder if I continue a little bit or if I save this for tomorrow. I think I still have a little bit of time, so I'll continue a bit. So now I'm just going to get into a specific case of what we just computed. So I'll discuss the case of a static particle detector in the Minkowski vacuum. Okay, so here, uh, what I have is that again, I will consider the detector to start in the ground state. Okay, and the detector's trajectory is going to be simply tau is just going to be tau, and then the spatial component is just fixed. Okay, all of them. All right. And remember that the final state of the detector that we computed before is going to be final state is, it was 1 minus P, C star, C, and then P, plus higher order, right? But then, as I just discussed with you guys, because Minkowski vacuum is a quasi-free state, we know that the one-point correlator is going to vanish, right? So because the Minkowski vacuum is a quasi-free state, then we know what? We know that C is going to vanish, right? So we know that the final state of this detector is going to be simply 1 minus P, 0, 0 P. And we also know that the third order correction is going to vanish, right? Because I just said that the 3-point correlator is going to vanish as well. All odd point functions are going to vanish. So I know that this contribution, the next order is going to be lambda 4. Okay. And then recall the definition of this probability of excitation was lambda square times the integral from minus infinity to infinity of the tau prime, and then this switching functions that I have, times e to the minus I omega tau minus uh, tau minus tau prime. And then I had basically this the Weidmann function computed along the detector's word line. So what I have is actually the pullback of the Weidmann function. It's going to be the pullback of the Weidmann function. Along the detector's word line. Okay. Uh, I guess in other words, I would say that basically what is happening is that the detector um, measures the vacuum correlations the vacuum correlations of the field, right? Of course, along its own trajectory, of course, along its trajectory. Okay, so we want to compute this pullback of the Weidmann function in our case. So for us, for this static detector, um, what is this pullback going to give you? This, if we look back into what we had for the Weidmann function in terms of t and x's, that's what we had, right? So let's look into this. So if I just have this, and now I need to plug the trajectory of the detector. So I know that t is going to just give you tau. So here I have tau minus tau prime, right? Tau minus tau prime. And then I know that the spatial coordinate is going to be the same, always the same. So this part is just going to drop. It's going to vanish. Okay. So what we have for P, so therefore what we have for P is going to be lambda square times the integral from minus infinity. I guess I can swap the order of this K integral here and the tau's the tau and tau prime integral. So I'm just gonna write this as this part first. Just copy this. Um, and then I'm gonna write the tau integrals. D tau prime times the chi of tau prime times e to the what I had there minus I omega tau minus tau prime times e to the minus I omega k tau minus tau prime. Okay, so I can rearrange this. I'll just rearrange here because I'm running out of time, so I'm just going to rearrange here again. So I can write this as e to the minus I omega plus omega k times tau times e to the I omega plus omega k tau prime. Okay. And therefore, if I define uh, Fourier transform as chi of omega equals to the integral from minus infinity to infinity of d tau times e to the I omega tau times chi of tau, then I can use this definition to write this probability as simply lambda square times the integral over k, which is going to be here 1, 2 omega k, 2 pi, and minus 1 of the norm of chi of omega plus omega k square. Okay, if you do this calculation, you're gonna see that that's what you get. So basically, I'm gonna have the final probability of excitation of this detector is going to be just the integral over this momentum space of this Fourier transform, the norm of this Fourier transform square. Okay, so I guess we don't have that much time, but maybe I wanted to ask you guys. So we saw that basically we started with some detector that was in the ground state, right? And yeah, we're measuring this P is actually telling me what is the probability of excitation. So what's the probability that starting from the ground state, I can reach the excited state for this detector? So what I'm telling you is that I started with a detector on the ground state and it was coupling with the field on its vacuum state in the Minkowski vacuum. And it's static. This detector is static. And I'm telling you that there is some probability, a non-zero probability, that it gets excited. So any intuition what could happen, or any intuition of possible situations in which this shouldn't happen, or in which limit this is going to vanish or not. You'd be nice if some of you said something, even if it's, I don't know, if you don't think it's correct. How on earth would this make sense? No ideas? Okay, so yeah. Yeah, I don't know is a good answer unless you're answering, someone is answering. Um, okay, so I guess one explanation, yeah, that's a guess, but I guess the best explanation here would be this happens both because of vacuum fluctuations being possible, right? So this property of this quantum system, and also the fact that um, we have some finite time switching functions. So, and why is that? Let's try to see what happens with if a detector is on forever. So if it is on forever, what it means is basically that the switching function is going to give you one. It's always on, right? And if you compute the Fourier transform of that, this is going to give you something that is proportional to a delta function of omega plus omega k. Now, we know that this gap, the omega, which is the gap, is something positive, and we also know that these frequencies are positive. So this means that omega plus omega k is a positive quantity. So this means that if I want to compute omega plus omega k equals to 0, this has no solution. So if I'm integrating this delta function under this integration, this delta function is going to vanish, right? Will give a 0. So what it means is, okay, so if the detector is going to be on forever, then the intuition is that it should not click. Okay, so the detector that is forever on will not click. So the probability of getting excited is just going to vanish. Now, if the detector is on for a finite time, for some finite time, then this probability is not going to vanish, okay? So if I have something that is on for a finite time, a general expression here, what I see is that this probability of getting excited is non-zero. So if the detector is on for some finite time, it will click, okay? So the probability of excitation is non-zero. And and moreover, actually what we find is that um, the shorter the time scale of this interaction, so the shorter the time scale of this interaction, the higher the probability of excitation. Okay, so what is the intuition behind this idea that, wow, if I have a very short time scale, there's a higher probability that this detector starting the ground state, despite being static, despite coupling to the vacuum state with the Minkowski vacuum, will still have some probability of getting excited. The intuition is that, well, if you have like basically a lot of resolution, so you can have a very small time scale, it means that intuitively you're adding more energy to your system. So you're disturbing the system more, so it's easier that you're going to get excited. So it's easier that your detector is going to see this excitation. That's the intuition behind it. I think you went a little bit fast in this final part. If you want, I can review this tomorrow a little bit. Um, but I'll stop the recording and then I will let you guys ask questions. Let me just see.